theorem of algebra. And identify solutions when our solutions are not always real numbers, because as we know, sometimes we have complex solutions and we need to know how to deal with those complex solutions. In the instance when we are able to have a combination of both real and complex, or all complex solutions. So let's take a trip down memory lane when we think about the imaginary unit I, which satisfies the property that if I have the square root of a -1, that is equivalent to I itself. Further, if I were to take the square root of -1, which equals I, and square it to release the radical sign, I squared is equal to -1, which comes from the property here. It is customary that anytime we see I squared, we always change it to -1. When I think about a complex number is consistent of a real number part and the imaginary part, which is the BI part. What's wonderful about imaginary numbers is that we're able to treat them just as we would operations with any other variables. So we can treat I just as any other variable. The only difference is anytime I see the I squared, I want to replace the I squared with -1. So be very careful in your homework about the operation in which we are trying to convey. So notice I have 1 minus 2I minus 3 plus 4I. This is not multiplication, it is subtraction. We know that with subtraction, I can get rid of our negative sign by distribution. This is the same then as 1 minus 2I minus 3 minus 4I, and then combining like terms. 1 minus 3 is -2, and then combining our imaginary parts, -2I minus 4I is -6I. However, we are able to distribute and multiply following the FOIL method or distribution. 1 times 3 is 3. 1 times 4I is +4I. -2I times 3 is -6I. And -2I times 4I is -8I squared. Combining like terms, I have 3 minus 2I minus 8I squared. But notice we have an I squared, so I'm going to replace this I squared with -1. Therefore, we have 3 minus 2I plus 8, where we are now able to combine like terms one more time. 11 minus 2I is our final solution. When I'm dividing, ideally what we're doing is rationalizing our denominator. Just like we don't like radicals in the denominator, we also don't like to have imaginary numbers in the denominator. Just like rationalizing, when I have a radical, we use the conjugate. We're also going to use the conjugate to eliminate the imaginary number as well. So when I'm looking at 3 minus 4I, we're going to multiply this by the conjugate. The conjugate then is the opposite sign, so 3 plus 4I over 3 plus 4I. Notice now we have a binomial times a binomial in our numerator and a binomial times a binomial in our denominator. So we will then distribute our numerator and distribute our denominator and see what might happen. 1 times 3 is 3. 1 times 4I is +4I. -2I times 3, -6I. And -2I times 4I, -8I squared. In the denominator, 3 times 3 is 9. 3 times 4I is +12I. Negative 4i times 3 is negative 12i. Negative 4i times positive 4i, negative 16i squared. A few things to simplify. I notice in my denominator that I have a zero pair, 12i minus 12i. I also know that I have 2i squareds, which I replace I squared with negative 1. Therefore, when I take 3 plus 8i, since negative 8 times negative 1 is positive 8, we will have 11 minus 2i all over. Here we have our i's were eliminated in the denominator because of a zero pair. I will also have 9 plus 16, since negative 16 times negative 1 is positive 16. Therefore, I have a positive 25. We've been able to conjugate the denominator by eliminating the imaginary number in that denominator. So our simplified form, 11 minus 2i. Let's continue practicing using our second slide. Here I have the square root of negative 3 times the square root of negative 12. I'm going to write a little note here that we want to simplify each radical first. Then multiply. If I simplify the square root of negative 3, I can't actually take the square root of negative 3 or 3 itself, but I can take the negative out front. Therefore, I'll have I times the square root of 3. The I is coming from negative 1 times 3. When I look at 12, I know 12 is the same as negative 4 times 3. When I take the square root of negative 4, we will have, we should put these in parentheses, we will have 2i square root 3. Now we can multiply. Remember, when we multiply radicals, we multiply the outside values first. So 2i times I is 2i squared times the square root of 9. We multiply the inside of our square roots. 3 times 3 is 9. This then simplifies to 2 times negative 1 because we replace I squared with negative 1. And the square root of 9 is 3. Therefore, negative 6. Most of that you most likely could do in your head, but just seeing all of the steps. Notice in our second example on this page, we have the square root of negative 3 times negative 12. Notice this time that these negative 3 and negative 12 are both underneath the radical, so we will simplify underneath first, and then we will go ahead and take the square root. This is the same as the square root of 36, since negative 3 times negative 12 is positive 36, which gives us 6. This last one is pretty interesting. We are multiplying together. Notice I've got x minus the quantity 1 plus 2i, and that's in brackets, and then x minus 1 minus 2i also in brackets. So I'm going to treat these brackets as a whole piece when I distribute, and you'll see why here in a second. I'm first going to take x times x. I know that's x squared. Then I'm going to take x times this negative 1 minus 2i. Therefore, I'm going to get negative x times 1 minus 2i, which seems kind of weird, but hold on. See it out with me here. Now I'm going to take negative times x times 1 plus 2i, so I'll still have the negative x with a bracket 1 plus 2i. Then finally, I'll have a negative times a negative, so I know that I'll have a positive, but I'll have 1 plus 2i times 1 minus 2i. And this will be easier to simplify doing it this way and then distributing one more time before trying to do a trinomial times a trinomial. Although you certainly could, you'll end up with the same result. This is just an alternative way that I find to be a little less messy. Now I'll distribute my negative x to each part here and here, as well as here and here. And then I'll distribute my two binomials at the end. So x squared minus x plus 2xi. You could do 2ix. I always put the variable first for some reason. Minus another x minus 2xi. And then let's distribute our two binomials here. So we'll have positive 1 minus 2i plus 2i minus 4i squared. There are some interesting pieces that happen now. I have a pair of zeros, so positive 2xi minus 2xi, as well as negative 2i, positive 2i. I also have this I squared, which I can replace with negative 1. Therefore, what do we have left over? I have 1x squared. I have a negative x minus 1x, and that's it for those. So I have negative 2x's. And then for my whole numbers, we have positive 1, and negative 4 times negative 1 is positive 4, therefore positive 5. Let's head to slide 3 to talk about the fundamental theorem of algebra. So suppose we have a polynomial function with a complex number coefficient with a degree that's larger than or equal to 1. Any polynomial that has a specific degree, we know has that many roots. However, in order to find all of those roots, we may need complex numbers to help us with that. Which leads us to the complex factorization theorem, which states that suppose we have a polynomial that does have complex number coefficients. If the degree of f is greater than 1, then f has exactly that many complex zeros, counting multiplicity. And we talked about multiplicity back in lesson 3.1. Note that the value of a above is the leading coefficient of f, and the polynomial is completely determined by the zeros, their multiplicities, and the leading coefficient. So it takes all pieces to make up the polynomial, all of the zeros, their multiplicities, and the leading coefficient to develop a polynomial itself. On slide 4, let's say that we are given the polynomial f of x equals x squared minus 4x plus 13. So I graphed it off to the right using Desmos, and we can see that there are no real solutions. So just going to make a note that there are no real solutions. We do know that we need two solutions. So since I don't see any real solutions, they must all be complex solutions. We're going to need to write our function in factored form, so we have a product of the linear factors, and we'll show you how to do that in a second. Well, I have a quadratic. I have no real solution, so I can't reduce my polynomial down using synthetic division. Therefore, we can use the quadratic formula to help us simplify this. Our a value is 1, our b value is negative 4, and our c value is 13. Therefore, x is equal to the opposite of b plus or minus the square root of b squared minus 4 times our a value times our c value all over 2 times our a value. Oops, and our a value is 1, not a. Let's begin simplifying. Therefore, 4 plus or minus the square root of 16 minus 52 all over 2. This is then equal to 4 plus or minus the square root of negative 36 over 2. I can take the square root of negative 36, but remember when we have the negative, that becomes the imaginary portion. I now have 4 plus or minus 6i over 2. The numerator is all divisible by 2, therefore 2 plus or minus 3i over 2. We have a common factor that we are able to eliminate. We have two solutions. Our two solutions are when x is equal to 2 plus 3i and when x is equal to 2 minus 3i. But it's asking us to write it in a product of factors. To do that, I can subtract everything in my parentheses over to the other side. Therefore, x minus 2 plus 3i, we're taking everything, is equal to 0. And x minus 2 minus 3i is equal to 0. Therefore, our function, written as a product of its linear factors, we can use brackets to that. Well, we can use parentheses. That'll be fine. X minus 2 plus 3i and x minus 2 minus 3i. Let's try slide 5. We have g of x is equal to 4x to the fourth minus 4x cubed plus 13x squared minus 12x plus 3. We need to have 4 solutions. And I know that one of my solutions is 1/2 because I graphed it and it told me so. Because it comes down and dips, I know that the multiplicity of this particular solution is going to be even. So perhaps 1/2 gets to be counted as a solution twice. And we also know that our solutions could be a combination of real and non-real solutions. Thus far, we know that x is equal to 1/2 with multiplicity of at least 2. So let's use synthetic division to break down our solutions even further so that we can get a reduced polynomial. I'll start out with 1/2 on the outside and then bring in my coefficients 4, -4, 13, -12, and 3. Always bring down 4. Half of 4 is 2. -4 plus 2 is -2. Half of -2 is -1. 13 minus 1 is 12. Half of 12 is 6. -12 plus 6 is -6. And then half of -6 is -3. Should not surprise us that we end up with the remainder of 0 because we know it is a 0. Let's do this one more time, because we know since it dips down and touches the graph that it has to have a multiplicity that is an even value. Let's try 1/2 again. So see if we can get another reduced polynomial, picking up where we left off. 4, -2, 12, and -6 always bring down the first term. Half of 4 is 2. So when we add, we have 0. Half of 0 is still 0. We have 12. Half of 12 is 6. Look at that. Comes out evenly. This now gives us the polynomial of no x's, x, and x squared, providing us with 4x squared plus 12. Well, we could easily solve this for 0 to find the other two solutions. I'll have 4x squared is equal to -12. X squared is equal to -3. Taking the square root of both sides, x is equal to plus or minus I square root 3. So that I portion comes out because of the negative. And we can't take the square root of 3. So here's our two solutions. The two other solutions. So half gets to be counted twice. So our solutions are x equals 1/2 and 1/2 got to be counted twice because it evenly divided here and here. We also had positive I square root 3 and negative I square root 3. So we have found all four solutions, but we still need to write it in factored form. So g of x is equal to, I'm going to leave a little space because we need to talk about that leading coefficient, x minus 1/2 squared, because there were two of them. Also, I have x equals 1/2, so to get it equal to 0, x minus 1/2 is 0, is where I'm getting the subtraction portion. I'll also have x minus I square root 3. From here, if I subtract, since x equals that, I'll also have x plus I square root 3. From here, if I add I square root 3 to both sides and set it equal to 0. I also, friends, I need to grab the leading coefficient and bring that leading coefficient down here as well. Because we have a complex solution, we need to use the same leading coefficient. It's also important to note that complex solutions always come in conjugate pairs. Let's try another example. I have x to the 4th plus x cubed plus 7x squared plus 9x minus 18. Put it in factored form. When I graph it, I do see, happy day, that I have two real solutions. I'm looking for four solutions. Therefore, since I only see two and I know that they're going directly through the graph, that there will be an odd multiplicity for each one. So if they are an odd multiplicity, it could be 3 times, 1 time, 5 times, etc. Let's just go on the assumption that it's only going to be once and see what happens with our reduced polynomial. So I do know that x equals -2 and 1 from looking at our graph. I can visually see that those are the real solutions. So I have 2 of them. We still need to find 2 more. If there are complex solutions, I know that I will find another 2 because they always come in pairs. So let's use find a reduced polynomial, dividing out each solution. So I'm starting with -2, but you certainly could start with 1 and then do -2. Either way, you're still going to end up with the same result, which is a really cool feature. Grabbing my coefficients, 1, 7, 9, and -18. Always bring down the 1. -2 times 1 is -2. So when I subtract, I have -1. Then I'll have +2, which is 9. -2 times 9 is -18. So I have a -9 times -2 is +18. Again, shouldn't surprise us that we end up with a nice 0 because it is a 0. I'm going to pick up where we left off with our reduced polynomial and divide out a 1. 1, -1, 9, -9. Always bring down the 1. 1 times 1 is 1. We get a 0. 0 here. So 9 plus 0 is 9. 1 times 9 is 9. Again, comes out nice and even with no remainders. Comes out nice and even with no remainders. This is our reduced polynomial. We have 0 x's, x, and x squareds. So x squared plus 9 is 0. So this would be pretty easy to solve. Subtract 9 from both sides, giving us negative 9. And then taking the square root of both sides, the square root of negative 9 will have x is equal to plus or minus 3i. So we do have an imaginary complex solution. Our 4 solutions then are negative 2, 1, 3i, and negative 3i. We need to put it in a pair of linear factors. Each of these only came across one time, so there's 4 solutions, so each one has a multiplicity of 1. Therefore, f of x is equal to x plus 2. Since if I wanted to get set equal to 0, I'd have to add 2 to both sides. X minus 1, x minus 3i, x plus 3i. Just like before, we do have a complex solution here, and because we have that complex solution, we need to bring down our leading coefficient, but our leading coefficient is 1, so we don't necessarily need to bring down that leading coefficient because multiplying by 1 isn't going to change anything. But just so you know, like getting in the habit, because of the complex solutions, we need to have and bring down that linear solution. Let's try another example on slide 7. Here I have 5 solutions since I have x to the 5th minus x to the 4th plus 7x cubed minus 7x squared plus 12x minus 12. So when I graph this, I see that x is equal to 1, and because it goes straight through, it could be a multiplicity of 1, it could be a multiplicity of 3, 5, etc. So I'm just going to start off by saying, well, I know for sure it's going to be x equals 1. And then I'm going to find a reduced polynomial. 1, negative 1, 7, negative 7, 12, negative 12. Bring down the 1. So I have 0. 1 times 0 is 0. So I have 7. Multiply to get 7. Add, we have 0, 0, 12, positive 12, and 0. All right, let's see if it's a multiplicity of 3. So let's try 1 again with my reduced polynomial 1, 0, 7, 0, and 12. Bring down 1. 1 times 1 is 1. 0 plus 1 is 1. 1 times 1 is 1. 7 plus 1 is 8. 8 times 1 is 8. 0 plus 8 is 8. 1 times 8 is 8. Oh dear. So 1 only has a multiplicity of 1 time because it does not evenly divide into it again. What that means then is that we have a polynomial here that we can look at in its reduced form. So we'll have 0 x's, so 12 will be our constant. X, x squared, x cubed, x to the 4th. So there's our coefficients. Our reduced polynomial is x to the 4th plus 7x squareds plus 12 equals 0. Now this looks like a quadratic, right? So what might multiply to 12 but yet add to 7? 3 times 4 works because 3 plus 4 is 7. I can then rewrite this as 2 binomials we will have x squared plus 3, and we will have x squared plus 4. Now, this might look a little weird to you, but do some side work to verify that yes, in fact, when I multiply these out, I end up with x to the 4th plus 7x squared plus 12, because x squared times x squared will give us x to the 4th. X squared times 4 will be 4x squared plus 3x squared, which is 7x squared, and 3 times 4 is 12. So if when in doubt, always double check. But now that we have it factored, we can set each factored piece equal to 0. So I'll have x squared plus 3 equal to 0, and we'll have x squared plus 4 equal to 0. And then solving each one, we'll have x squared is -3. And if we take the square root of both sides, we'll have x is equal to plus or minus I square root 3. Again, they come in pairs. And then if I subtract 4, we'll have -4. Take the square root of both sides. Therefore, x is equal to plus or minus 2i. So we have two solutions with plus or minus I square root 3. Another two solutions with plus or minus 2i, and then a real number solution all together. So what will this then look like? So first of all, we have a leading coefficient of 1 here. We have complex solutions, so we need to bring that coefficient down. I know that this isn't going to make any difference to writing it as a linear factor, so I'm not going to worry about putting the 1 in front unless you desire to do so. But in its linear form then, h of x is going to be x minus 1, because I know that I need to subtract 1 from both sides, so x minus 1 is 0. I'll also have x minus I square root 3, x plus I square root 3. I'm going to run out of room, so I'm going to tack it on down here. I'll also have x minus 2i and x plus 2i. All of these have a multiplicity of 1, but I do have 5 factors, 1 for each exponent. I could put the 1 here if I really wanted to, because it is a complex solution, but not necessary since it's a 1. We have x to the 4th minus 2x cubed plus 27x squared minus 2x plus 26. Given that x is I, is one of the zeros, write in factored form the solutions. So when I'm looking at the graphical part, I have absolutely no real solutions, but I am given x equals I, and I know that complex solutions always come in conjugate pairs. So not only does x equal I also know that its complex conjugate, that x equals -I, is also a solution. So let's use I and -I to reduce the polynomial into something that we are able to work with. So I'm first going to divide out I. I have 1, -2, 27, -2, and 26. Always bring down the first term. So 1 times I is I. Now be careful here. I can't just take -2 and add I to it and make it like -1I or whatever you might come up with. It is -2 plus I. So now when I take I times this next set, I will have I times -2, so -2I, and I times I is I squared. We know we can replace I squared with -1. Now when I add these together, I can add my whole number parts together. I therefore still have -2I minus 26. Now I'm going to take I times -2I, which gives me -2I squared, and therefore I have +2, since I times I is I squared, and I squared is replaced with a -1. And then I have I times negative 26 or negative 26i. When I add these together, we can also add our whole number part. So I have 0 minus 26i. I'm sorry, 27 minus 1 is positive 26. So this would be positive. I apologize for that error. So I have positive 26i. So I times 26i gives us 26i squared, which is negative 26, since I squared is replaced with negative 1. And 26 minus 26 is 0. That's a lot of steps there. So be careful. If you need to write out more steps, please feel free. I'm now going to use our reduced polynomial here. That kind of looks a little weird with all of those i's, but it'll clear itself up once we divide out the negative I from the reduced polynomial. So I have 1, negative 2 plus I, negative 2i plus 26, and 26i. Always bring down the first. So 1 times negative I is negative I. When I combine like terms, all I'm left with is negative 2. Negative I times, so we're multiplying, not adding, we're multiplying. Negative I times negative 2 is positive 2i. Again, when I combine like terms, look how it's clearing itself out. I have positive 26. I times 26 is negative 26i, and we have cleared it up. Our now coefficients are 1x squared minus 2x plus 26 set equal to 0. I'm not going to be able to factor this because I don't have any real solution. So there's nothing that's going to multiply to 26 but yet add to negative 2. We are going to need to utilize the quadratic formula to help us. So A is 1, B is negative 2, and C is 26. X is equal to the opposite of B plus or minus the square root of B squared minus 4 times our A value times our C value, all over 2 times our A value. So 2 plus or minus the square root of 4 minus 104 when we multiply, all over 2. This is going to turn out pretty nice. So 2 plus or minus the square root of negative 100 over 2. 2 plus or minus 10i, since the square root of 100 is 10 and the square root of the negative is the I value, all over 2. Notice that all of these values are divisible by 2. They're all divisible by 2. Therefore, 1 plus or minus 5i. We now have our solutions. X equals I, X equals negative I, X equals 1 plus 5i, and X equals 1 minus 5i, but we need to put it in linear factors. Just like I did the last example, I'm going to put these in parentheses here so that when I get subtract them, I can subtract the whole unit. So mx in its factored form of linear factors is x minus I from here, x plus I from here, x minus 1 plus 5i from here, and x minus 1 minus 5i from here. All of them have a multiplicity of 1. We have 4 factors. We needed to find 4 solutions. As a reminder, the leading coefficient is 1. We did have complex solutions. The leading coefficient is 1, so we would need the leading coefficient here to be 1. However, not necessary because multiplying by 1 doesn't change anything. And the last solution, or the last example on slide 9, Create a polynomial with real number coefficients which has all the desired characteristics. You may leave the polynomial in factored form. It tells us that the degree is 5, so we need to have 5 solutions. It tells us that x is equal to 6, x is equal to I, and x is equal to 1 minus 3i. This is outstanding. However, that's only 3 solutions and we're going to need 5. But notice that we have 2 solutions which are imaginary solutions. So if I have x not only equal to 6 and I have x is equal to I also have x is equal to negative I, because we know complex solutions come in their conjugate pairs. Also, if I have x is equal to 1 minus 3i, I also have x is equal to 1 plus 3i. Now when I count them, 1, 2, 3, 4, 5, I have a polynomial that will have degree 5. My solution then, f of x, we're going to come back to this bullet point here in a second. So if I get x together and set them equal to 0, we will have x minus 6. We'll also have x minus I. If I add I to both sides, we'll have x plus I. I'll also have, like I did on the last example, when I've got these binomials that are complex, I'm going to take x minus this whole part, so x minus 1 minus 3i, and x minus 1 plus 3i. All of them have, again, multiplicity of 1. Now looking at our solutions, it says that as x is approaching negative infinity, our f of x values, our y values are getting positive. So the left behavior is going up. It doesn't give us any indication if the right is going up or the left is going, or the right is going down. Therefore, our a value or our leading coefficient could be a positive or a negative value based on our lesson from lesson 3.1. So I'm only going to just put an a here. We're going to have a leading coefficient of some kind. That leading coefficient could be 1, or it could be a variety of different solutions, such that it could be a positive or a negative. We're not sure. All it's giving us is the left endpoint. It's not giving us the right end behavior. But this concludes lesson 3.4. It also concludes all of Unit 3 together. Please reach out with any questions that you might have.